I see there was just another question posted on Slido, but maybe that person, if they're here, or maybe Johan can find it in Slido and answer it there. Our third talk is by Derek Chen and his colleagues from Google DeepMind. So if he could come up.
Hello.
Hi. Excellent. Derek is going to present, and his colleagues are going to present 2 tried and tested techniques used at Google for efficiently learning high-quality data representations, multi-size unified embeddings, and architectures for learning effective feature process.
Hey, what's up, RecSys? How are you doing? So we're from Google DeepMind, and I'm Derek Chung, and these are my colleagues, Ben Coleman and also Wang Chenkang. And so we're stoked to be here to share our learnings on efficient data representation learning. One sec, I think we've got to pull the slide deck.
Yeah, where is it?
How do we present? Okay. Full screen? Yeah, full screen. All right, how do we present? I forgot.
I did too.
Yeah. Because somehow I forgot how to present. Are we good? Yeah. Okay. Oh, the clicker. Yeah. All right, let's get started. So today we're going to talk about efficient data representation learning. And so during the pandemic, we have seen the crazy rises for the financial market. And so people were yelling, stocks only go up, and to the moon on Reddit and on Facebook and Twitter. Actually, sorry, Meta and X. And so in a way, the machine learning community was hoping for the same. So models only go up in sizes. And so in a way, it was right. And so having faster computation, cheaper computation, also just tremendously bigger data sets. And our model sets are getting bigger and bigger, and actually they're doing better and better as well. And so the question was could the party continue? And unfortunately, the answer was maybe no. We also saw the severe chip shortage during the pandemic, and so it kind of slowed down the party a little bit. And also, I'm sure a lot of people have seen this. There was a point you can just simply making models wider and deeper and to get sizable gains, but it was no longer the case. So naive scaling no longer works. And so it's really calling for research to build models that are much, much more efficient, and in the meantime, just deliver more bang for the buck. And so our angle is coming from efficient data representation learning. And so we decompose the problem into 2 subproblems. So first we have our input data, and we feed our input data into embeddings. And so these are essentially embedding tables. And then we feed the embeddings into a feature cross-learning network, and to learn interactions between different features. And then these get fed into a network to make the final predictions. And bear with me here. So data representation learning is a crucial for machine learning problem. I'm a golfer, so I'm going to make a bad analogy for golf. And so it's essentially like how important golf grip is to a golfer. And so let's just say the club and the contacts we're seeing as a golfer is your data and is our input. And so our model here is just say Tiger Woods, the GOAT for golf, amazing model for golf. And so then the golf grip is essentially how you hold your golf club. It's the only contact point between your input data and the model itself. And so let's say we have an amazing machine learning model like a Tiger Woods, and with a shitty golf grip like mine. And so even a Tiger Woods amazing model is going to hit shitty shots and make horrible predictions. And so this also happened to be a multi-billion-dollar problem, if not double-digit billions. And learning data representation is actually really easy for humans, but hard for models. And so there are a lot of issues for the current solutions for embedding learning and for feature cross-learning. So for embedding learning, the default solution is sort of the random hashing with one-size fit-out tables, and so there's huge space waste. And on feature cross-learning, so there are a lot of solutions trying to improve, but just they fail to deliver just on more model expressiveness without compromising on efficiency. And it turns out it's really hard, really challenging to improve on top of it, even though some of these solutions are not perfect. And so one example would be random hashing for embedding learnings. I'm sure a lot of people use random hashing for embedding learning in your systems. And in Google, it's been the best we had for over 10 years. And so it was there for a reason. It was very hard to improve on top of it. And in the meantime, it's very hard to push on the creative frontier for both efficiency and accuracy. And in the meantime, imagine being us, and so we have to build highly generalizable solutions to work across different distribution, different data systems in Google. For example, extremely dynamic short video recommendations or billions of items in ad systems. And in the meantime, we also have to build solutions that can handle Google traffic and also severe latency requirement. All right, without further ado, I'm going to hand over to my colleagues, Ben, to talk about embedding learning.
All right, thanks, Derek. I'm Ben, and I'm going to talk about our work on embedding learning. Before I do that, though, just want to say thank you. This is not an individual effort. We've got a ton of contributors and collaborators across Google. They're all wonderful. All right, so here is a typical recommender model. We've got a bunch of inputs, categorical or discretized. We use this to index into an embedding table and then feed the embedding to the rest of the network. Now, embeddings are the first and the biggest component of our models. And so we have to worry about things like hash collisions. If two values collide in an embedding, the model can't tell the difference between them anywhere downstream. We also have issues related to high churn rates, dynamic vocabulary distributions, and power law distribution of the features. We might have, for example, poor representation in the tail due to not much learning examples, or collision with a head element, which wipes out that representation completely. I'd also like to point out that these models are huge, like on the order of 10 trillion parameters, and 99% of these parameters are located in the embedding table. This causes a really big systems and algorithm challenge, in addition to the modeling problems. Oh, and we oftentimes have hundreds of these embedding features, so we've got to do a lot of work to represent our features. Now, there's been a lot of academic work over the last 20 years on this problem, and I won't go through all of it, but something I'd like to highlight is just that industry companies, Google, Meta also has an accelerator. We've developed hardware accelerators to accelerate that 2009 baseline. And the reason why we've done that is because, as Derek said earlier, it's a really hard problem to improve on. Very few methods actually transfer from academic experiment to production. Now, I'd also like to highlight that when we do research on this problem, we're interested in the parameter accuracy trade-off of our methods. This is because we can usually improve performance by increasing the memory. We can't do that arbitrarily because of serving cost. So this trade-off lets us understand what will happen to our performance if we don't increase the serving cost. There's also a nice modeling intuition here. If we're getting better generalization for a specific parameter budget, we're in some sense learning a more representative embedding because we're getting better parameter efficiency out of our model. All right, so the method that we've developed that improves on, shows practical improvements in prod is called unified embedding. And mechanically, it's really simple. We just take all of the features and stick them into the same embedding table. The hypothesis here is that this will reduce collisions by indexing into a massive indexing space. If we want variably sized dimensions, we can just look up multiple times and concatenate. And we have methods to make this really systems friendly for our accelerators and other systems problems via sharding and load balancing tricks. But why do we expect this to improve the trade-off? Well, first, it's going to reduce collisions within a single feature. Because we're taking these two cities, for example, and we're indexing them into a really big range, it's going to be much less likely that these things are forced to share a representation. But hey, you might be saying, what about cross-feature collisions, right? What if this item ID has to share a representation with a weekday? And so what we found here is that, yeah, this does happen, but it's not very detrimental because of a behavior that we've discovered called the multiplexing mechanism. It means that different features can share an embedding space without an appreciable loss in quality. And this happens intuitively because the model can process a single embedding using different parameters in the downstream model. Of course, the practical takeaway here is that we end up improving the parameter accuracy trade-off. And the important thing here is that we improve it for almost all of the points on that trade-off. This is important because our production models live on various points there, so we want to be sure that our method will improve a given model in a given application. And that's actually what we see. So what you're looking at here are 5 applications across search, ads, and recommendation. Got a pretty diverse layout of applications here. We've got products, short-form video, app recommendation. And what we're seeing is some very significant results. Oftentimes 10 times the significance threshold for our large-scale A/B tests. This is all done without increasing the model size, so we've been able to launch this in over a dozen products, and we've served billions of users using this kind of method. We'll take questions at the end, but for now I'm going to hand it off to Wang Cheng, who will talk about the next component in our representation learning arsenal.
Hi everyone, I'm Wang Cheng. I'm Wang Cheng from Google DeepMind, leading the embedded learning efforts, working closely with Ben and Derek. So today I'm going to present on behalf of RecSys Wang, who led the efforts in feature cross-learning and unfortunately can't join us today. So feature crosses are quite important and have been widely used in recommender system. For example, back to the old days, imagine we have a linear model to predict whether the user is going to purchase the blender. Then we will have features like whether the user has purchased banana, whether the user has purchased a cooking book. So these are first order single features. So normally we will have add some cross feature to capture the interaction between features. Let's say whether the feature has purchased both banana and a cooking book. Then this cross feature can be very effective for the predictive model. However, this is still a very challenging problem, especially how to efficiently and effectively capture those important cross. Nowadays, we use more neural networks for recommender system and ads CTL models. So we are handling embeddings, and we consider feature crosses among embeddings. However, traditional neural network can implicitly learn the feature cross to fuse the embedding together. But actually, we found it's very inefficient and can only do it in an approximate way. So how to resolve this? There are 2 common remedies. First is we use larger, wider, and deeper network to model the complex crosses. And another way is to leverage both the explicit feature crosses and the implicit feature crosses capability from DNN. There is a line of work in leveraging both explicit and implicit feature crosses for recommendation and PSTL models. And RecSys and the team has also been proposed methods like DCN. However, in practice, we found it's still very challenging to land these ideas in production model. So to this end, RecSys and the team have made several critical improvements for putting DCN into practice. And it's been very influential nowadays. So this is the framework of DCN v2. So we have 2 different architecture. The left one is a stack architecture, and the right one is a parallel architecture. So basically, it's a fuse of the cross layers and deep network. where the cross layer provides the explicit feature cross capability, while the DNN product provides the implicit feature cross capabilities. So how does a cross layer look like? So it's actually very easy to implement and very straightforward. So we have the feature cross matrix W, and we multiply it with the embedding. And then finally, we use element-wise multiplication to get our final feature cross results. With a little bit of math, we can prove that with a L-layered DCN, we can capture all the feature interactions up to L plus one's order. And we also consider feature interactions in the sense of both bit-wise and feature-wise. So we also made some other technical improvements in DCNV2, such as we are using a mixture of expert layer in DCNV2. So please refer to the paper for more details. Experimental results-wise, we have achieved the SOTA results, and very interestingly, we found that if you properly tune the baseline DNN, it actually performs very, very strong. So DCN has been very, very influential, both internally and externally. So it reaches over 50 launches across major products across Google. It's open sourced, and it's been included into MLPerf benchmark. We also heard a lot of successful stories from other companies. So I will hand over to Derek to conclude the talk. Thanks.
All right, just to quickly wrap up. And so I hope you agree with us that this is a really important problem and a freaking hard problem too. And so in the meantime, we developed our one-two punch solution, essentially serving as the go-to solution for efficient data representation learning in Google. And so looking ahead, and we love to leverage all the benefits coming from large language models. And we firmly believe that the embeddings could serve as the bridge to connect the best of both worlds of traditional RecSys models, large embedding models, and large language models. Next slide, please. All right, that's all we have for today. And thank you so much. And we're open for questions.
Thank you for your presentation, gentlemen. There are 2 questions already on Slido, and I don't see any in the room here. So someone asks what the typical percentage of collision is for one feature space. Maybe that's a question for you. Yes.
Oh, that's an interesting question. Yeah. You want to take it, Wang Cheng, or? Yeah, I'll take it. Okay. All right, sure. So depends on whether you're in academia or production. In production, we are typically limited by the embedding table size. So there's actually a significant number of collisions. Like, I can't put an exact percent on it, but it's probably more than 5%. In academia, your vocab sizes are a lot smaller for academic data sets, so you can get away with much, much smaller collision rates.
Okay, thanks. There's another question. Do you have any evidence that DNNs can only approximate feature crosses? Approximate to what extent?
Yeah, you want to take this one?
So yeah, DNNs can learn feature crosses. And so it takes 5 layers of ReLU to learn second-order feature crosses, and takes 19 layers of ReLU to learn third-order feature crosses. So in a way, they're extremely inefficient. That's why there are a lot of work just trying to focus on different kinds of feature interaction learning capabilities.
Okay, thanks. No questions from the audience still? Then I have a final question. I think we have time for that. You write that the optimal architecture for feature cross learning is highly data dependent in your paper. Can you say a bit more about this? Like, what kind of properties of the data set or the domain influence this? Are there any interesting patterns here?
Yeah, as we said, like for L-layered DCN, it will capture L plus one order of interactions. So it really depends on how complex the data is, right? How complex, what kind of interaction we are trying to capture. So if the data is relatively sparse, then normally we will capture like a lower order interactions would be enough. Otherwise, if it's very dense and rich data sets, then we might need to have a more complex and a deeper
across the layer to capture the crosses.
Okay.
I can add a quick just follow up. And so essentially, DCNV2 was working with totally different kinds of distributions in Google, and we have corpuses that are sort of 100,000 candidates, essentially small vocab features. And in other corpuses, we have features that are 1 billion items. And so it's proven to be working really extremely well and highly generalizable across different systems.
Okay. Thank you very much. I think that's it for questions. So thank you again to all the speakers.